Okay, hello everybody, or nobody, depending on how many people are watching this video. Today, I am going to explain to you something called particle physics. And particle physics is, well, it has a fitting name. It's the physics of particles. And it's not a very well-known subject, but it really isn't that complicated. Well, at least the basics of it aren't. And I've yet to find a good YouTube video that explains all of the basics in one video. At least in my opinion. So I'm going to make one. It's probably going to be cheesy and low quality, but either way, I'm going to do it. Okay, so let's go ahead and get started. So this right here, it's a little bit blurry because my camera's not perfect, but this right here is the standard model of elementary particles. And elementary particles are particles that cannot be divided down into anything. So generally, with normal reactions, elements are the smallest things that you can get. But behind those elements, those are composed of protons, neutrons, and electrons. And electrons are elementary. I'm not sure, I don't think you can see it, but this right here does say electron with an E to abbreviate it. So electrons are elementary. They cannot be divided. However, protons and neutrons can be divided into these up here, which are called quarks. So you probably can't read it, but that's okay. So this says quarks, this says leptons, because the orange ones here are the quarks, these blue ones here are the leptons, these red ones here are the bosons, at least the elementary ones. I'll get to that later. And this is the Higgs boson. It's technically not a boson, but it's weird the way that it works. Okay, so let's go ahead and get started. So let's start with these quarks. So there are 6 kinds of quarks. There's the up quark, the charm quark, the top quark, the down quark, the strange quark, and the bottom quark. And the strange quark has very strange properties. So I'd say they gave it a fitting name. And so quarks, essentially, they are what compose hadrons. So hadrons are particles that are subatomic but not elementary. And hadrons can be divided into 2 categories: baryons and mesons. Now, this is spelled M-E-S-O-N-S, and I've heard them pronounced mesons, and that's the only pronunciation I've heard, but I way prefer the pronunciation mesons, so that's just how I'm going to pronounce it. So we have hadrons that are baryons and mesons. And so, again, hadrons, these are not elementary, but they are still subatomic, so they're not as big as atoms, but not as small as elementary particles. So let's give you a couple examples of baryons. So you have probably heard of both of these. I'm assuming that you have a basic knowledge of chemistry, at least if you are watching this video. One common baryon is the proton. Yes, it's a very common baryon. In fact, it's pretty much probably the most common baryon, but I don't know. Either way, it's pretty well known. It makes up a lot of matter as we know it, and this proton is composed of quarks, specifically 2 up quarks represented by 2 U's and 1 down quark represented by a D. And so if we look at this, well, as I said, the camera is blurry so you can't see it, but I promise in the top left corner of each of these is a little number, and that number represents that particle's charge. And you cannot take away that particle's charge. That particle will always have that charge. So, as you can see, as you can't see, all of these particles have charges. And so, in the top left of this, that's the up quark, it says 2/3. So that has a charge of 2/3, assuming that a proton has a charge of 1/3. Okay, right, as I was saying, protons are composed of 2 up quarks and a down quarks, and a down quark represented by U, U, D. And so, an up quark has a charge of 2/3, whereas a down quark has a charge of -1/3. So, the charge of a hadron is the sum of the charges of all the particles that are contained within it. So, let's do some quick math. So the up quark has a charge of 2/3. The next up quark also has a charge of plus 2/3. That is 3/2, which is not what we want, 2/3. And then down quark has a charge of -1/3, so -1/3 do some quick math. 2/3 plus 2/3 is 1 1/3, minus 1/3 is 1. Hence, why a proton has a charge of 1. So, we can represent it as this little circle with 2 U's and a D. Look at that. You can't see it, but I promise it's amazing. Now, another common baryon that you have probably heard of is a neutron. So, a neutron is composed of 1 up quark and 2 down quarks. So, again, as I said before, the sum of a particle is the sum of the particles that are contained within it. The charge of that. Yes, so you get the idea. So, this up quark has a charge of 2/3. The down quark has a charge of minus 1/3, and again, the other down quark has a charge of minus 1/3. Let's do some quick math. 2/3 minus 1/3 is 1/3. Minus 1/3 is 0. Hence, when a neutron has a charge of 0. So, if we add this all up, so let's make a little diagram. 1 U and 2 little D's, and a fantastic little circle. So there's that. And if you might notice something about these. These are both hadrons, and they're both baryons. And there are many different kinds of baryons. You can make them with all of these quarks, and some of their antimatter versions, and I'll get into that in a second. But the thing is, they both have 3 quarks, and that's generally the thing with baryons. They have 3 quarks. Technically, the rule with baryons is that they have 3 or more quarks, but ones with 4 or 5 quarks have just been theoretically proposed, but never really confirmed, and plus they don't really matter. So generally, baryons have 3 quarks. Now, mesons, on the other hand, which I'm just going to pronounce as mesons. Let's see here. So mesons have 2 quarks, and there are a lot of mesons, just like there are a lot of baryons. And so let's use one example of these mesons. A pion. This wonderful pion contains an up quark and an anti-down quark. We represent this anti-down quark with a U and a D with a line over it. The D is, the line over it means antimatter. And antimatter, it sounds scary. It sounds like, oh, antimatter, it's going to destroy us all. No, it's not. Antimatter, it's exactly the same as normal matter. It just has the opposite charge. So let's say we have an up quark that has a charge of 2/3. Well, an anti-up quark has a charge of minus 2/3. That's it. Everything about it is exactly the same. So in this case, we have a down quark, which has a charge of minus 1/3. So the opposite of that is going to be plus 1/3. So we have 2/3 for the up quark, plus, not minus 1/3 for the anti-down quark, which is going to end up to be 1. So this pion has a charge of 1. It's incredible, isn't it? 1. Here, let me draw another little diagram for our little pion. It's going to have an up quark and an anti-down quark. And part of the thing that makes antimatter sound so scary is if there were like a galaxy full of antimatter, that's okay. Everything's going to function just fine. But the thing is that by themselves, matter and antimatter are perfectly normal. They're fine. It's just the thing is, when they collide, they react, so to say, very explosively, and I mean very explosively, like an up quark, an up anti-quark, just come on, yeah. Okay, anyway, right, as I was saying, let's have another meson. This one is known as the Pion. One thing I like about particle physics is everything has cool names in it. Anyway, so a kaon is composed of an up quark and an anti-strange quark. So, as you may remember, the line over that S represents the fact that it's antimatter, which means that it has the opposite charge than it normally would have. So if you look here, this strange quark has a charge of minus 1/3, and the antimatter version of that would have a charge of plus 1/3. So, this strange quark, so let's do the math. 2/3 for the up quark plus 1/3 the anti-strange quark is 1. How incredible. Let's draw ourselves another nice little diagram. An up and an anti-strange quark. Alright, so that's generally the rule. So there are hadrons, which are particles that are subatomic but not elementary, and they are divided into baryons and mesons. Baryons have at least 3, but generally only 3 quarks inside them. Mesons only have 2 quarks inside them. So, and there are many more baryons and mesons than the ones I just showed you, but these are the most common ones and the most well known. And these are not all stable in a vacuum. In fact, the proton is the only one. Not even a neutron is stable in a vacuum. But I mean, it's a long story. I'll explain all that later. Actually, I probably won't explain all that later. But anyway, right, let's get on to this. So now we've covered quarks on the standard model. Now let's move on to the leptons. And the leptons, there's a lot to say about them, but a lot of it I don't know, and it's just not that interesting, at least in my opinion. You can do your own resources. Maybe I'll make a video about the leptons later, but as of right now, there's not a lot to say about them. There's the electron, the most well-known one, the muon, and the tau, which are basically exactly like them. There's the electron neutrino, the muon neutrino, and the tau neutrino, which are just like their counterparts but neutral and apparently theoretically infinitesimally small. But I'm not going to get into philosophy and theoretical, actually I already am in theoretical physics, but I'm not going to get that far into it. So, anyway, right, so quarks are quarks, leptons are not very interesting, and if you ask me personally, I think that these bosons are really interesting. And there's 4 of them. We have the gluon, represented by G, the photon, represented by gamma, which is like a little curly Y, the Z boson, represented by Z, and the W boson, represented by W. Now, so let's go over what each of these are one by one. Actually, first I'm going to cover something else, very quickly. So there are 4 types of fundamental forces in the universe. There's not really any reason that they happen outside of crazy quantum mechanics. They just do. They just exist, and we can't entirely figure out why yet. And so these are, what are they? Yes, these are the strong force. Sorry, I'm trying to write this quickly. The weak force, yes, they are actually called the strong force and the weak force. I did not name them. The electromagnetic force. Hang on. This is taking a while. And good old gravity. So, now, the strong force, to put it simply, is what keeps quarks together. So, similar to gravity. Gravity, it sticks things together, but the strong force, it doesn't just clump them together. Whereas gravity, it'll just stick anything into a giant ball of crazy radioactive plutonium or whatever. The strong force, it's at least, it's more organized. It's going to keep them organized into nice, neat hadrons. And so that's what the strong force does. That's what it is. It is the thing that keeps hadrons together. And so, however, it doesn't just exist by itself. It is carried. It is carried by a wonderful little particle called the gluon. This is the particle at the top of the boson column, whatever you'd call it, and it's represented by a G. And so yes, so the strong force, to put it simply, is carried by the gluon. The gluon contains this strong force. It's embedded inside the particle permanently, and so if the strong force is what keeps these together, then, you're going to need gluons inside those. Hence why they're called gluons. They glue quarks together. So these models, they're inaccurate. We need little g's in there between the quarks to make it more accurate. Because this, so yeah, the gluons, there's also going to be gluons inside there, because otherwise it would just be, gravity would take over and just clump it, or the weak force, or the electromagnetic force, probably gravity would take over, clump everything together, and the universe would not be very interesting. But that's why the strong force is a thing. And like forces and physics. Anyway, right. Wait, are we recording? We better be recording. Oh, thank goodness I'm recording. Right, yeah, yes. And so that's the gluon. The gluon carries the strong force and keeps quarks together, hence why it's called the gluon. It glues quarks together. Next up is the photon. And the photon, you've probably heard of it. It carries the electromagnetic force. It's, again, like the gluon with the strong force. To put it simply, it's embedded. I've said it to put it simply too many times, but anyway, it's embedded inside the photon. It's just the photon has that force inside it, and that force is, well, it can be a lot of things. For the two most common are light and radio waves. So to put it simply, as I am receiving light billions of times per second through my eyes, those are photons hitting my eyes and receptors going through my brain. But first things first, the photons have to hit my eye, just as photons have to hit that camera, and photons are going from your screen to your eyes. And so photons, they are light, to put it simply. I said to put it simply too many times. I need to come up with something to put it simply, I need to come up with something better to say. That was funny. Anyway, I'm getting carried away. Now, we have the next up, we have the Z and W bosons. I'm going to group these together because they carry the same force, the weak force. The weak force is carried by the Z and W bosons. And weak force, to be completely honest, I don't completely understand it myself, but really it just keeps things together. No, sorry, that's gravity. It's what causes radioactive decay. The Z and W bosons cause, I just said it, it's what causes radioactive decay. I don't understand it myself. I'd love to do more research about it and make another video on it. But for now, that's the extent of my knowledge on them, other than the fact that, and by the way, it's worth mentioning that the W boson, there are two identical versions of it. The W plus boson and the W minus boson. They, one has a charge of one has a charge of -1. Other than that, they're exactly the same. There's also the Z boson, which has a charge of 0, and so do the other bosons. However, apparently the W boson is called that because it carries the weak force, and the Z boson is called that because it has 0 electromagnetic charge, and that's pretty clever if you ask me. So those are the Z and W bosons. I don't entirely understand them. In gravity, as far as we know, no particle carries it, but if they find a particle that does, they better call it the graviton, because that sounds really cool. Anyway, now, so that's all of that covered. Next up, I'm going to cover the Higgs boson. And the Higgs boson is really interesting because it doesn't you heard nothing, because it doesn't behave like any other particle. And it's not exactly a particle, and if it is, from my understanding, it has no mass, it has no volume. Or if it does, it's infinitesimally small. It's just, if you keep measuring it, you're going to keep going. If you could stay there for eternity measuring it, and you never find it. It's there, but it's infinitesimally small. That's if that theory is correct, and my understanding of that theory is correct. Which, I mean, there are a million places that could go wrong. So let's start. And the Higgs bosons, if this theory is correct again, they are. It's the second time I've done that. They are everywhere. And this everywhere of Higgs bosons is called the Higgs field. And the Higgs field is composed of Higgs bosons. I just said that, didn't I? I did, dang it. Anyway, so let's say this right here is the Higgs field. Okay? This is the Higgs field. It's Higgs bosons everywhere floating around. So each of these particles, other than the Higgs boson, has a definite mass and volume that is constant and cannot be changed unless you're a nuclear physicist living in a concrete bunker with nothing better to do. in that case, then do whatever you want. But for most normal people that are sane and live normal lives, then it's good, they're going to be the same. And so, what causes this? Why is it that they have that? The answer is, if this theory is correct, it's because of the way they interact with the Higgs field. So this is the Higgs field, and so let's say, I'm going to use an electron for example. Let's say there's an electron floating around, just minding its own business. Well, why does it have the volume it does? Why does it have the mass it does? Why is that? The answer is because of how it interacts with the Higgs field. Let's say there's this little sphere where it interacts, pushes out of the way these Higgs bosons, or sucks them in. We don't know. I don't know. To put it simply. I said that again. Anyway, so these electrons are just floating around, and let's say this is the Higgs boson. It's just doing its thing, but inside here, this is the electron. It's pushed the Higgs bosons out of the way in that certain area, and that's what causes it to have its mass and volume. It's just nothing where it would be something. So that's what causes it to have mass and volume that it does. Of course, there's basically no way to prove that, but there's basically no way to prove that that's not true. So, who knows? I guess we'll find out in the year 2070. Hopefully I live long enough to see that. Anyway, so there's the Higgs boson, and last time I recorded this was my second take. I stopped it here, but since then I have learned more things, and I added some numbers in the top right, and these are called spin, and spin is very, very complicated, and I don't entirely know what it is, and the truth is, nobody entirely knows what it is. So I'm going to explain to you the simplest theory that I have heard myself. I found it incredibly easy to understand. There's no saying if it's true, it's probably not, but I'm going to explain it to you anyway because it's the best understanding of spin I could find. But please keep in mind, don't go on telling you people, oh, this is the truth about spin. No, it's not. It is an answer that's probably false. It's the most easy to understand one. So keep that in mind. Now, let's proceed with the things. Right, spin. So, every particle has a spin, and a spin is assigned to that particle, kind of like the charge is assigned to the particle. It just is. It's on it permanently. You can't, take it off. No, it's just on there. As is its spin, and its spin is very surprisingly how much it spins in place, according to this theory. So, let's say I used an electron last time. Let's use an up quark. Let's say we have an up quark right here, and it is floating around. Well, it can be pushed by something. Say a down quark. This down quark's going to push it, and the up quark's going to move because Newton's laws and stuff. However, that's always the case. It's always going to be, it can move. However, it needs to, influenced by other particles and other forces. However, as far as its rotational momentum, how much is rotating in place without actually moving, that, according to this theory, is its spin. So let's say this is an up quark. It's going to spin around this much. It's going to keep doing that for all of eternity until, well, who knows what. But it's just spinning. It's spinning so much. And so all these particles, the quarks and the leptons, are considered fermions, however you want to put it. They have a spin of 1/2. And however, bosons all have a spin. So let's say there's a gluon. Gluons, I'm going to represent this by more arrows to represent that it's going faster, have a spin of 1. That's not entirely true. These are going to have half integer spins. Quarks are going to have, fermions are going to have half integer spins. Bosons are going to have integer spins. So there's that. And the spins are, keep in mind, that is the simplest theory about spin. It's not entirely correct, probably not anyway. So who knows? Don't go on telling your friends about that this is definitely the truth and we're all going to die in 2022 because aliens are going to come and abduct Elon Musk or something like that. No, that's not what I'm trying to tell you here. So that's essentially more or less what spin is, if this theory is correct. I'm going to stop saying that. But there's one last thing I'd like to explain to you. So let's go back to the very start. Hadrons. So right, hadrons are divided into baryons and mesons, right? Okay? And so let's look at this proton. Let's make a bigger model of it. Right here is going to be kind of cut off because I only have so much room here. But so here's one up quark, here's another up quark, and here's a down quark. Alright, pretty simple. That's what I originally told you. Then I introduced gluons. And then I left it at that. So this is an ideal, simple proton, right? This is what a proton would theoretically look like. It's not. Let's say that a strange quark and an anti-strange quark just so happen to be, floating around doing their business. So let's draw those in. They're thinking, oh hey, look at this. This nice particle is going to let me in. So they're going to go join it. However, because nothing about this is affected, not its spin, not its charge, nothing. There's essentially no way to tell that this is different from a normal proton, or it is a normal proton essentially. That's what it is, because there's nothing affecting it. It's just that there's these two strange quarks in here with gluons holding them to the other quarks. Now, let's say, I swear if this happens again, let's say that there's a charm quark, and I don't know, let's say an anti-top quark. That sounds interesting. Again, add all those charges up, it still equals 1, which is normal of that of a proton. And let's say there are some gluons. Oh my gosh, you gotta be kidding me. Again, so let's say there are some gluons holding those together, right? So there's that. That's just holding that together. And so there might be those quarks in there. And maybe there also happens to be a bottom quark. And an anti-down quark. Again, these aren't going to influence anything. And so it's still just a normal proton. And more gluons are going to float around here. And let's say, as I was saying earlier, photons are flying around everywhere. They're being emitted by electrons. They're crazy photon shenanigans. So there are probably going to be some photons somewhere in there. So let's draw a couple photons. And radioactive decay happens, so there might be some Z and W bosons in there too. And so in reality, an idea, a proton is as simple as this: up quarks, down quarks, and gluons holding them together. And yes, that is what a proton would ideally look like. But in reality, they would look. You can't see it because of the light. Here, does this help? That does not help in any way. There, you can see that a little bit better, not very well still, but that is closer to what a proton would actually look like. Of course, realistically, there's no way to distinguish between this proton and this proton. They behave exactly the same. Who knows? Maybe these two protons are bound together in an atom of helium, along with this neutron and some other neutron. That might also be crazy. So, in reality, protons are not simple. They're crazy conglomerations of particles. Alright, that's really all I want to explain. Now, of course, I haven't covered everything perfectly because I'm 12 years old. So, 12-year-olds are essentially incapable of covering everything perfectly. But I'd say I did a good job. So, please like if you liked it and subscribe if you subscribed it. Yeah. Okay. Thank you for watching, and please remember that this is important stuff, kids. Whee!